In this video, we'll explore a seemingly simple problem, coloring a grayscale image, and in the process, we will uncover some of the deep and fascinating mathematical concepts that underpin computer vision. Let's begin by defining our terms. What exactly is a digital image? A grayscale image has a single channel of information where each pixel is assigned an intensity value, typically ranging from 0 or black to 255 or white. These 256 shades of gray create the shapes, textures, and light that our eyes perceive. In contrast, a color image typically uses three channels, one each for red, green, and blue, with each channel also having a value from 0 to 255. This gives each pixel over 16 million possible color combinations, which our image viewers interpret as a single, unique color. It's worth noting that while we'll focus on the popular RGB format, other color spaces like LAB and YCB-CR also exist. These are often used because they better separate a pixel's lightness from its color, which can be useful for different applications. Now, back to the problem at hand. Given a grayscale image like this, can we find the one correct colored image? While we might have a specific image in mind, from a mathematical perspective, it turns out that many different color images are all equally valid. To understand why, let's look at the inverse problem, converting a color image to grayscale. There are different formulas for this, but one of the most common is a weighted average. These specific coefficients aren't arbitrary. They are a direct result of how our eyes perceive light. Our eyes are most sensitive to green light, less sensitive to red, and least sensitive to blue, which is why the green channel gets the largest weight, followed by red and then blue. This simple formula reduces each pixel's three color values into a single gray value. Algebraically, we can immediately see the issue. We have one equation with three unknown variables, r, g, and b, so there is no unique solution except at the extremes of 0 and 255. For a given grayscale value, there is an entire family of r, g, b combinations that satisfy the equation. Let's visualize this geometrically. Each pixel in a color image is a point in a three-dimensional color cube with the red, green, and blue axes ranging from 0 to 255. The grayscale image, however, exists on a single one-dimensional line. The conversion from color to grayscale is a transformation that projects every point in the three-dimensional RGB cube onto a single point on this one-dimensional grayscale line. We can notice that an entire triangular plane, defined by the equation, which slices through the RGB cube, collapses onto a single point on the grayscale line. Every point on that plane, regardless of its unique R, G, and B values, results in the exact same grayscale value. This means that the conversion from color to grayscale is a lossy process. We fundamentally lose information, and because of this, a true inverse is impossible. This leads us to an interesting detour into the world of information theory and lossy compression. Grayscale conversion is a form of compression, as it reduces the data required for each pixel by a third. It's not typically used as a compression mechanism, but rather in applications where color information isn't necessary for the task at hand, say for reading text from a scanned book or detecting tumor in a medical image. Let's look at some less drastic form of compression. For example, what about quantization in the RGB space? We could change the range of each color value from 8-bit to say 4-bit. We would still lose information, but because each channel is still there, the inverse looks much more realistic. Let's return to our problem statement of coloring a gray image. So we know all these are mathematically correct, but what is it that makes some of them look unnatural? Look at this example. What makes it different from a natural image is the jaggedness in its local regions. We don't expect neighboring pixels to have such random, jarring color shifts. In fact, if we take all the pixel values in a natural original color image and plot them in our RGB cube, we'll see localized clusters. This is because real-world objects are continuous and usually smooth in terms of their color and intensities. Our regenerated image, however, while being mathematically accurate, does not possess this smoothness or continuity. This brings us to the concept of high-dimensional data distributions. The actual dimensionality of an image is astronomical. For example, a 1000 by 1000 pixel image with 3 RGB channels has a dimensionality of 3 million. Imagine a 3 million dimensional space where each point corresponds to a unique image. But almost all of these images would look random and unnatural like this. Natural images, on the other hand, lie on a much lower dimensional manifold embedded within that space. This is called the manifold hypothesis, and it's a core idea in machine learning. It states that even though data may exist in a very high dimensional space, the meaningful instances of that data, such as natural images, human speech, or well-formed text, do not randomly fill that space. Instead, they lie on a much lower dimensional manifold embedded within it. To understand a manifold, imagine we have some three-dimensional data where each sample has three values. When we plot this data, we might find that the points aren't scattered throughout the three-dimensional cube. Instead, they all lie on a thin surface or sheet, embedded within that space. That sheet is the manifold. The data only occupies this small, continuous surface, not the vast, empty space around it. So, we want to ensure our generated color image has this kind of smoothness. But there is another issue. How do we ensure grass is green and water is blue? A model or algorithm that only learns continuity in neighboring pixels might produce a perfectly smooth image. But it could assign a bizarre color like pink to an entire body of water. This is because it lacks a high-level semantic understanding of the world. This is where a world model comes into the picture. A world model is a higher level understanding of objects and their plausible colors. It knows that grass is green, the sky is blue, and skin tones fall within a certain range. The model's task, then, is not to magically invert the grayscale conversion, but to find the intersection of two geometric objects, the triangular plane of infinite solutions, and the low-dimensional manifold of natural images. By finding the solution that lies on this manifold, the model finds the one that conforms to its learned model of reality. This is exactly what deep learning models trained for this task do. A common architecture used for this, a type of convolutional neural network, or CNN, called a U-net, is perfectly designed for this task. Convolutional neural networks have an inherent inductive bias that makes them well suited for image data. Their use of small local kernels assumes that nearby pixels are related and that a pattern found in one part of the image can be found anywhere else. The U-net architecture has an encoder-decoder structure. The encoder learns abstract, high-level features, effectively creating a compact, latent representation of the world model. The decoder then reconstructs the final color image from this representation. A crucial feature of U-nets is their skip connections, which directly link layers in the encoder to corresponding layers in the decoder. This allows the model to transfer low-level features like edges and local textures, thereby preserving the image's continuity and fine details. By training such a model on a large number of natural color images, it learns to approximate this complex inverse problem. The model doesn't just learn to fill in colors, it learns to identify which of the infinite possibilities is the most plausible by simultaneously learning a low-level continuity prior and a high-level semantic world model. To recap, what began as a simple problem of converting a grayscale image to color led us on a journey through linear algebra, information theory, and the geometric structure of high-dimensional data. We learned that the solution lies not in finding a unique mathematical inverse, but in using an internal model of the world to navigate a space of infinite possibilities and find the ones that are both plausible and consistent.